uploaded the lab 3. So here is your lab 3. As usual, you're going to do with your similar teammates. Okay, teammates which is dah banyak kali kan, it's already frequently that you did together with your team. So I hope there is no problem coming out. Maybe there is a sleeping partner or maybe yeah. So hope that everything is okay. And for lab 3, as usual, you need to come out with one is report. Please upload it in terms of PDF file only. Okay, there is one thing that I don't want you to do is, maybe after this I'm going to put a mark. Don't zip whatever RAR, whatever type of folder. Don't zip your answer. I don't want you to zip your answer, although it is PDF, PDF and also MP4 inside. I don't want. Please make sure you upload it one by one. One PDF and another one is your MP4 and whatever type of video that you're going to upload. If let's say, as usual, if let's say your video is too long, you can upload into your YouTube and put it the URL into your PDF. It's okay, but don't zip, because if zip, I need to download everything. I don't want. For video, I can download because I need to watch, of course. That's why I really like for those who make it on YouTube, because I can like later on watch it directly. So for lab 3, you will needed to do several parts as usual, and as usual also you need to answer all these part A, part B, and part C. So you need to answer everything in terms of the PDF report. Your answer should be similar to your team member, but not in terms of different members and different group. And about the video, again, you need to come up with one video. Just pick any question you like. So I'm going to be flexible at it kind of things, which is you can pick a question for part A, or maybe you can explain for part B, or maybe you can choose to explain part C, depend. As long as it help you to speed up your submission, as long as I can help you to reduce your works, especially when you need to submit many things throughout, like your project still not yet finished. You need to focus on your final exam later on. So I hope that you can pick any question, but please make sure all team members are included, and might be it's good for you to open the camera, so that I know who are talking instead of just voice. As mentioned last time, it's happened for by your seniors. There is someone that copy that video directly without any changes. They just adding extra background music, then it upload and submit to the lab submission. So they fought in my class, so I don't want it to happen. So please make sure you record the video by yourself, not taking from others. So in terms of part by part, you can see here, you need to draw the JK flip-flop index. I do believe most of you familiar already using the DIT simulator. So simulate using the tables that given. So everything here is quite simple. You just follow the step by step. But you can see for your part B here, you need to design the synchronized counter you were given with scenario here. So yesterday also yesterday or this morning also I bumped into several questions that your friend WhatsApp me. Still I didn't have finished to scroll down. I don't know what happened. Okay. There is a lot of you asking me question. So from this type of question, there is one of your friends ask me, can they come out with that scenario? Can they come out with this scenario? So I said yes, because you are free to create your own scenario. This is your own scenario. You have own input, you have your own output. And in terms of initial, whether it is empty or not, how many of the maximums you have. So all these scenarios you need to clearly state in your report. As long as you clearly state in your report, so I can accept. Okay. So you can see here, might be you can come out and use the different scenario, or maybe you just change in terms of, might be this one is basket here, maybe you can come out into different type of fruit, or maybe fish, or maybe whatever things. Then you can just change it and put it into your project. So it's slightly similar. So you, instead of doing lab 3 and different project, so you can come out with different things from your lab 3, but instead you need to change a little bit, of course, in terms of scenario. For the here, maybe it is fruit, for you to calculate how many fruit inside. So you change only the background of the scenario. So you can use the similar circuit for your project. Okay, so that is not going to burden you to come out with different type of synchronized counter. So this is synchronized counter. And for your part C here, you need to analyze the synchronized counter following the pictures given here. So you need to put it into your DIT simulator. You follow basically the similar drawing, and you need to come up with what next step table here. And you need to come out with all the answer and justify. That is on your lab 3. I give you about like 30 minutes. So did you finish, go through? Any question related to your lab 3?
Doctor, about part A. Questions 3 and 4. Is the answer for each question of those, do you want them like in sentences or in graphs, drawings, or anything? Like, is there a specific format?
3 is sentences. And yeah, you need to justify, but not in you need to justify this in terms of your answer in sentences. And identify whether JK flip-flop in is positive. Yeah, this one also. Sentences. Which graph? Doctor. Which graph you see?
Because I thought like, you know, similar to the questions 1 and 2, I thought like maybe drawing some kind of things on it.
No. For 3, you need to justify which stage that you have in terms of JK flip-flop, but it's not SR. I think this one is very easy. And identify the positive, yeah. This one also, you need to identify this JK flip-flop for 7, 4, 6, 7, 6. Is it positive trigger or negative trigger? You cannot just like answer, okay, this is a positive edge trigger, but in terms of you can answer positive edge trigger, but you need to like, okay, because of blah 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 might be. So you have a short explanation on that. Okay. So any other question? So if not, we can move to our next.
Doctor?
Yes.
May I ask about the video we should present of the paper?
Paper? What paper?
This lab.
This lab, okay.
We should present all part.
Okay, for video, I ask you to just pick any question. Okay, janganlah you pick yang ini. Don't pick like drawing. So I said all team member means that it's quite long question. So might be in terms of this simulation. So one part A might be, so one student explain question number 2, and maybe question number 2, 2 student explain. Maybe question number 3, 1 student explain. And lastly, question number 4, another 1 student explain. Okay.
Okay, all right. Thank you.
So you pick your own, which one that you want to present for the video. Okay, any other question? I not take note here. Give me some time. Let me edit first. Okay, don't zip, okay? Let me proceed with our cascade counter. This is your new things. I ask you to do and to try all other synchronized counter. Question, did we cover this? Yes, right. Because I remember this one is, I still not cover for only section 09. Okay, let we continue with cascade counter here. Okay, this is only the recap for you to remember about your modulus last time. So what is modulus? So you need to have 2 the power of n here. So if you still remember, this is a numbers of flip-flop that you need. Okay, so modulus 8, you need 3 at least. There is a common modulus. If you still remember, it is a modulus 10. It called a BCD and blah, blah, blah. You can try to find out this again, just to recap for you in terms of a modulus. Last time we already covered. So in this specific subtopic, we're going to look into cascade counter. Counter can be connected to achieve higher modulus operation. So cascade means that the last stage of output of one counter drive into input of the next counter. So you have here example, when you have 2 counters modulus 4, 2 counters which is modulus 4 and also modulus 8. So this is one counter, this is another one counter, and it is connected in cascade, can achieve count until 32 clocks, which is modulus 32. How you come out with this is by multiply 4 and 8 here and all together you're going to get 32. 32 is numbers of clock that you can achieve. So here is an example when you have modulus 4 counter. If you still remember again, when you have modulus 4, you have 4 equal to the power of n. What is n here? 4 equal to the power of 2. That's why you have 2 flip-flop here. And here when you have modulus 8 to the power of 3. 3 is a numbers of your flip-flop here. This is modulus 8 counter. And cascade is when you have 2 counter connected together in terms of cascade. This output will be connected to be a next clock for your next counter. Okay, so this is the hint here. It will be connected to the next counter clock. Okay, example here, you want to have modulus 10 counter. So instead, you can see here, modulus 10 counter using 2 cascade decade counter. So you have equal to 10 times 10. This counter can be viewed as a frequency divider. So you know now this is a frequency divider. It can use also as a frequency divider. It divided the input clock frequency by 100. So you can see here, this is frequency clock that you feed in. And first, because you have 10, you're going to divide with 10. And then when you have all together, finally, you're going to have 100. So you're going to divide it, your frequency, your total frequency in at the first beginning with 100. So total mode is 10 times 10, you're going to have 100. So this is an example how your connection look like. And when you need modulus 1000 counter, you have 3 cascade decade counter forming a divide by 1000 frequency divider. So you have here 10 times 10, you have 100, times with another 10, you have 1000. So basis clock frequency of 1 megahertz, and you wish to obtain, okay, you can read this. So this is how you can get. And about the frequency, if you have at the beginning of 1 megahertz, you're going to divide with 1000. Then your final frequency will be 1 kilohertz. Because over here, when you have 1 megahertz, here it will be 1 megahertz divided with 10. And then you divide this, your answer here, 1 megahertz divided with 100. And then 1 megahertz, you divide with 1000. Then you will get, here is time 10 to the power of 6. Here is 10 to the power of 3. So you're going to have minus 3. Then you will get 10 to the minus of times to the power of 3. This is called as 1 kilohertz. This is mathematics terms. My battery is calm. Patutlah. Where are? Okay, here there is a exercise for you to try and test. You can see here 2 type of counter. You have counter 4 and counter 8. Need to be used to achieve count up for modulus n. This one you don't know yet. And n clocks. This one in terms of frequency also you don't know. How to cascade the counter to achieve counter until 32 clock, modulus 32. So it is easy because you can just times 32. What is the frequency produced by each counter for initial is give you here. So you're going to have 18 megahertz. So here might be you're going to come out with what 18 megahertz divide with 4 first. And then it fit in, it's going to be 80 megahertz. You're going to divide with 32. 8 times 8 here, 32. So what is the answer? So that is how you're going to justify in terms of how you're going to cascade, because it similarly looks like this. 4 and 8. And each of here is going to be CLK divided with 4 here. Altogether 4, 8 times you're going to have CLK divided with 32. Okay, now any question about this new cascade thing? How you can come up with your modulus 32, modulus 10, modulus 1000. So everything is already given here. And there is exercise you can try here. Maybe you can try around, play around with the numbers of the modulus. Okay, here there is a 4-bit synchronized binary counter. So there is a dedicated counter IC, which is 74HC163, which is a mod 16 counter IC. The starting counter sequence can be changed by setting the initial value at D3, D2, D1, D0. So this is the data input. To load the initial value, load must be 0. So you can see here there is a several scenario that already provided. It mentions that your load bar here normally must be 0. So here must be connected to the ground. So what next here? This is the type of 4-bit synchronized binary counter. This is the looks. So you can going to see at each pin. You need to remember at each pin. Okay, pin number 1, it is connected to CLR. Pin number 9 is connected to load. So what is the connection? So you need to know, okay, this is connected to a ground. So this is ENT, this is ENP, this is clock, what pin number. So sometimes there is also a question to ask in your MCQ part A related to each pin. Might be said, okay, what is the connection for pin number 7? What is the connection for pin number 1? So it's good for you to know each pin what is the connection to for your 4-bit synchronized binary counter. Okay. Next we have here. We have cascade counter with transcaded sequence. This cascade counter below has 16 the power of 4. So you can imagine how big is for your counter here. So you have 65, 536 stages, full modulus for 4 cascade. We call it as C for cascade, T for transcaded, R is what? CTR, transcaded. And then you're going to have DIV, which is you're going to divide it. I rasa I ada something lah. Wait someone is calling me because after this I have open day for. I will change the password. Okay. So here we have CTR DIV 16. So this is for cascade counter with transcaded sequence. This is the look here. If we have, we need a modulus 40,000 counter only. So how? If you just need this. So you having this cascade 16. So how are you going to do? So first, you need to determine the initial value, which is this is the value that you have, all the full modulus that you have. And then you just need 40,000. So here you have this kind of value. You can also try to check this one is in terms of your hexadecimal. Okay. Second, therefore, preset cascade counter is to the 63C0 hexadecimal by setting the value of your D3, D2, D1, D0 as shown below. Okay. You have the D1, D3, D2, D1, D0. So you have all this value. This is mask getting have setting up. You can see LSB, and this is your MSB connected similar to your normal counter using flip-flop and etc. It must be from LSB to MSB. But this is decade. Okay, this is decade. That's why it's put D. So you can see here, this must be your 0. This will be your C. This one is LSB, MSB. And this will be your 3. And this will be your 6 here. How you get this? By getting the value total of these full stages minus with 40,000 depending on the equation. If the equation asks you to have like 30,000 only, then you're going to have 30,000. When you have the value, this is in terms of decimal. You convert it into your hexadecimal. Because what? This is base 16. This is your called as CTR DIV 16 because you have all this cascade counter 16 to the power of 4. This is 16, 16, 16. That's why if you have the power of 4, you're going to have all together is 65,536 stages. And This value 0 will be here, C, 3, 6. And you can see here, as mentioned last time, although final exam will be covered only 7 onward, but remember I told you sometimes there is a knowledge still you need to remember, especially now in terms of numbering system module 2. You have 0 hexadecimal. How are you going to convert it into binary? How you have C in terms of hexadecimal, you're going to convert to your binary here. This is C in terms of binary. This is 3 in terms of binary, 6 in terms of binary when you convert hexadecimal to binary. Okay, so you have all those input value, and this will be also asked in your final exam. So now we're going to move to analysis of sequential circuit. Analysis of sequential circuit, there is step by step that before you can analyze. Step number 1, you need to derive the excitation equation from the starting of your logic schematic. If you have the logic schematic like this might be, okay, example. So you need to have following the step by step to analyze your schematic. Second, when you have the derivation of your excitation equation, of course, you're going to get your Boolean expression. So here you're going to jump to step number 2. You need to derive next state and output equation. Next state table and the output equation. Third, generate the next state and output table. Okay, from here you have the next state, you have the output equation, you're going to create the table. And after that, you have to generate the next diagram. So the diagram that you last time already learned how to draw. And step number 4, you need to develop the timing diagram. So let's check in terms step by step. So this is step number 1. Start with your logic schematic from which we can derive excitation equation. So step number 2, this one is also similar already mentioned here. So this is example that you can have SR, JK, D, and T. How you get this in terms of the flip-flop characteristic equation. And then step number 3, and lastly step number 4. Okay, we look into example. Analysis of sequential circuit, we were given with the modular 4 counter. So this is example, and normally we will given the kind of this circuit. So might be we're going to ask a few questions related to this. Okay, example modulus 4 counter here. Derive the state table, state diagram for the sequential circuit below using the method number 1. Method 1, modular 4 counter. So step number 1, you are going to come up with derive excitation equation. So from here, how are you going to derive your equation in terms of D0, and D1. So where is your D here and D here? You have D0 and D1. So you need to find out how to get the equation. So you look at this side. What is the connection here? So after that, you're going to get CNT exclusive O Q0. Isn't it? You can see here. This is connected to your D0. And this is your XO. First input is connected to your Q0. And another input will be connected to your CNT. Okay, so this is first that you can come out with for step number 1. Step number 1 again, but it is okay. From this you can derive. This one you already learned in terms of your module 1 and 3. So please make sure you still remember. It is related to A, B, A XOB. If you still remember, it's also similar to A bar B plus A B bar. So it's also similar to here. Okay. So we look into the next one is our D1. D1 is here. We can see it's connected to the OR gate here. And all the OR gate have 3 inputs. O will be plus. So here are connected to AND gate. Here are connected to AND gate. Here are connected to AND gate. But if you still remember about the equation from your Modulus 4, last time you already learned everything here. If you check back your modules, then you know you can come out directly with here without looking here because you already memorized. But it's okay, we can do it slowly one by one. So for N here we have, let me draw first plus with plus because I have 3 input. Here, here, here. I don't know what is inside. I need to check first here. This is AND gate. This is AND gate. This is AND gate. For first one, I have the input of Q1. Q1. And another one is CNT bar. Okay, you can see here. Okay, done. It's finished. Second, I have 3 inputs. First input will be my Q1. Second input will be my CNT. And third input will be my Q0 bar. Okay, this is my connection. And lastly, I have 3 input also. Over here, it will be my Q0. This one is Q1 bar and another one is CNT. So I have all these. I put everything here. It should be similar. Q1 bar. Okay, correct here. Why there is no bar at this part? QZ. Kenapa I put bar here? So I have, it's all correct. This is correct, and another one is also correct. So this is my Boolean expression for each input flip-flop in our schematic. Step number 2, I need to derive the next state equation by converting this excitation equation here into flip-flop characteristic equation. In the case of our now is flip-flop, D flip-flop. So in this case of D flip-flop, Q plus equal to D. What is Q plus? Next. Q next, right? You have, if you still remember, your next output for your Q is always depending on your D. 0 will be 0, 1 will be 1. You remember this table? So that's why it's summarized that it is equal to D. So Q0 plus, this is another next step, is 0 first, and then you will be having another one, which is Q1 next, and etc. So here you have Q0 next. You have also Q1 next, because you can see here you have Q0 and Q1. So from here, you have this similar value here, and this is putting here. And after that, we're going to come out with the step number 3, construct the next step table. From these constructions, you have the next step tables. This is your next step table for D1 and D0. So you put every value depending on what you will be having the similar value with D0 and D1 here. That's why your next step table is similar. And then after that, you can come up with your state diagram, which is you will refer to your next step table. From this state, it goes to the next state. From this state, you're going to go to the next state, and etc. So how it look like? You can see there is a several input here. 0, 0. At this state, if the input is 0, you're going to go to here. 0, 0. If you have the input of 0, you're going to go back to 0, 0. Second, you have 0, 1. 0, 1, and then you're going to go to 0, 1 also when you have the CNT go to 0. Similar to others, is going to go back to its states here, you can see. But if you have the input CN, T is 1, 1, 1, you're going to see from 0 it's going to go to 0, 1. From 0, 1 is going to go to 1, 0. From 1, 0 is going to go to 1, 1. And lastly, from 1, 1 is going to go to 0, 0. So this is the looks of your state diagram from your next step table. Alhamdulillah. So next, where is it? Okay. Here you can see that the state diagram is generated directly from your state table. Lastly, you're going to come up with timing diagram. So you're going to have your circle and look back your flip-flop. Is it positive edge or negative edge here? It is a positive edge, so you're going to trigger when you have a positive. Q1. Okay, this value, how come we get this value? You're going to look into this equation here. You can see, because it's already given that Q next, Q next will be similar to your D. That's why it's similar to from step number 1. So you get here. And all this value, you're going to compare. You can see D0 here. If it is 0, you have the value of Q and T is 0. Q1 is not here. Q0 is 0. It's 1 plus 0. You get 1 here. So that's why 0. We have C and T is 0. 0, you get 1. 1 times 0 is called 0. Okay. And then you have 0 here. You can see, you put the value inside, then you will get the answer here. Second state here, you can see, if you have here 0, and then your Q0 is 1. 1.1. 1.1 plus, you have here 0.1 bar, you get 0. So you still have 1. That's why you get 1. So you just fill in the value inside the equation you have. You can come out with the next table, and you can come up with your state diagram, and lastly your timing diagram. So your timing diagram, you're going to trigger when you have the positive clock. And you have the C and T value. Where is your C and T? You're going to look into this is your C and T value. And you have the diagram like this. This will be your next timing. This is your timing diagram following your clock and C and T, if your C and T were given like this. So your Q1 is depending on the value of your Q1. You can see here, you're going to start with 0. You check your value whether here will be trigger or not. So it's not going to have any trigger at your clock there. Second, you have CNT is 1. When you have CNT of 1, you can see you're going to change the value, but you're going to trigger only at the positive clock. When you have the 1 here, your Q0 at the initial one is 0, 0. So you have 0, 0. You're going to jump to 0, 1. 0, and then you have 1. At this side, it shows you that there is a several gap here. If you still remember, it's tagged several times, but it is really small, like a nanosecond. Sometimes you can't see, so you can just directly put here. And what next? At this positive clock here, you can see you have previous value is 0, 1. So you are at this side. Check your CNT value. If CNT is 1, you can see you're going to move to 1, 0, 1, 0. So there is a microsecond on gap. Normally last time we just directly goes up, right? But it is very small in between. It's going to be teranjaskan, which is there is several gap between these. Okay, next we're going to have a next positive clock there. So here your previous value is 1, 0, 1, 0. So when you have CNT is 1, you're going to move to 1, 1. And lastly, here at this side, you're going to have 1, 1 before this, and then, okay, now it's already 0, 0. So if CNT is 0, what happened is going to be always revert back to 1, 1. So that's why it's similar like this. Okay, any question for this step by step? So you need to remember another step. See, there is a lot of steps that you need to remember. Here is another five steps that you need to remember. Okay. So here, you can also have, this one is just a summarization of this example, similar one. Okay, we have another example in terms of another method, 2, which is using a JK circuit analysis. Just now, method 1 is using D. Now here we have JK. Similar method, you have 5 methods altogether. So you're going to come out with the equation first. How about your J1, K1, J0, K0. All of these will have their own value. And you're going to see here there is slightly different. Just now you didn't have this output. But now for your JK circuit analysis, you're going to have the output Z using method number 2. So this is the equation of the Z from this schematic diagram you have. After you have this step number 1, you're going to come out with the next step table first. From this next step table, you're going to fill in the value by using these methods. You just put X is 0, Q0 is 0. What will happen for J1? It will be 0. What is happen for your J0? The value is given already. So you fill in. And how about your next state? So you're going to have the next state of, you just fill in the flip-flop JK transition first. And then when you have the value here, you're going to refer back to your excitation table and you get the value of your Q1, Q0. Following your diagram here. Q1, Q0, you're going to refer to the value of this. Then you're going to fill in the value of Q1 plus, Q0 plus. And step number 4, you're going to draw the state diagram. After you have the state diagram, you're going to come up with a timing diagram. So it is slightly similar. Okay, this one is the example. Okay, continues over here. Okay, this one is D flip-flop. So different. So the rest is only for your exercise. You can try to do it 2 exercise, 15 and 16. You can try to use your DIT simulator also. This one, you can see this is slightly similar to your lab 3, but there is several changes there. So any question? Tomorrow we're going to come out with our last module. Where are I point? Module 9. It is not too many, but I hope that I can cover all in Module 9. If not, we're going to have like a video recording. And after that, we can focus with our exercise back, recap back whatever we have learned throughout our from Module 1 until Module 9. Because although final exam cover in terms of your Module 7 upward, but still a lot of other necessary things that you need to remember back. Okay, from your others. Any question? So related to your project due date, I think next week I'm going to inform you. Before final exam, I want you to submit. But the date is not yet announced because I want to give you extra time to do with your friend after you finish all your lecture from other subject also. So any question? This evening I have class, but I need to attend the postgraduate open day. So any question? If no question, we're going to stop our class now and we meet again tomorrow morning. Okay? Okay, thank you.